Welcome to the advanced topics for Lecture 2.1, Kitchen Table Electronics. Let's begin in talking about fields and potentials with the fundamentals, Coulomb's law. Coulomb's law says that the force between 2-point charges, labeled here 1 and 2, is equal to 1 over 4 pi epsilon 0, the dielectric or the permittivity of free space, times the product of the charges on the 2-point charges, divided by the square of the distance between them. And I'm going to put up here a unit vector r12 to remind us that the force is a vector quantity. The fact that the force is a vector quantity means that the force on any one charge, owing to all the others, can be calculated as a vector sum of the forces between pairs. This is called the principle of superposition. It becomes useful when we want to define a quantity called the electric field at some point, and we will define this as the force on a unit charge. So now we have the sum for all I other charges of Qi over Ri squared, and of course there is a unit vector I connecting the ith charge to the charge test charge at the origin. The units of the electric field then are force per unit charge, or newtons per coulomb. Now, the unit charge doesn't have to be a unit of charge. It can be an infinitesimal charge that we scale up to get the electric field. The reason for making this point is that, of course, we don't want our test unit charge to disturb the distribution of charges around it. So here we've defined the electric field in terms of the force on a unit charge from all the other charges surrounding it. From this definition of electric field, we can go over to a continuous distribution of charge and field and consider the flux of a field at some point over a surface. And this will be a surface element with a normal pointing perpendicular to the surface at the point at which the integral is calculated, and we integrate this over the whole surface. So this is defined to be the flux of field out of a surface, and from this definition here, it follows that this is equal to the charge contained within that surface divided by epsilon 0. This will be familiar to you as Gauss's law. We can put Gauss's law into differential form, where now, rather than the charge enclosed by some area, we consider the charge density at some point r. The result is then that the partial derivative of the x component of the field at point r with respect to x, plus the partial derivative of the y component of the field at some point r with respect to y, plus the partial derivative of the z component of the electric field with respect to z at some point r is equal to the density of charge at that point r divided by epsilon 0. We can write this expression the following way in shorthand by saying that the divergence of the electric field is rho over epsilon 0. And this is the electric field at any point r, the density at any point r. This is the differential form of Gauss's law. Now, the electric field is a conservative field. What this means is that if we consider any 2 points in the field, and we calculate the energy expended in going from A to B, and then back again by any other path, we obtain 0. This is because all of the forces times the distance elements along this path will be equal and opposite to all of the forces times the distance elements along the return path. Because of this, we can define a potential difference between these 2 points A and B, where the symbol phi here stands for potential. So, phi at some point B minus phi at some point A will be equal to minus force times distance. So it is this integral here of E at any one point along the path dot an element of length along the path, force times distance on a unit charge between the points A and B. And that's the work done per unit charge. So it's work over charge or joules per coulomb. These are the units of potential. It follows from this integral definition that we can define the electric field as a gradient of a potential, i.e. the electric field at any point r is given by minus the gradient of the potential, and this gradient operator is just a unit vector x times d by dx plus a unit vector y times d by dy plus a unit vector z times d by dz. Now, this is the work done per unit charge. If we define the work per unit charge as the volt, so joules over coulombs are volts, then the units of the electric field, since it's the gradient of this potential, are volts over meters.